The history of computers and why they work in binary. One day I was lecturing about the ENIAC, Electronic Numerical Integrator and Computer. It's considered the first electronic general-purpose computer. It was created during World War II by John Mauchly and John Eckert, and its purpose was to calculate firing trajectories for artillery shells. Given the weight of the shell, the amount of the powder, and the angle of the barrel, how far will an artillery shell travel when fired? And where will it land? Suddenly it hit me. Holy smokes! It's the game Angry Birds. The core of Angry Birds is, given the weight of the bird, how far back the slingshot is pulled, and the angle of the launch, how far will the bird travel when fired, and where will it land? Although it appears computers were invented and built for the military, maybe video games were the real reason behind the digital revolution. Two important lessons emerged from the ENIAC project. Number one, ENIAC did decimal arithmetic. It manipulated base 10 numbers, not binary numbers. Number two, ENIAC was programmed by moving wires and switches. It did not store its program in main memory. Just after the war at Princeton's Institute of Advanced Study, John von Neumann started work on the IAS computer. It did binary arithmetic, manipulating ones and zeros, and also stored its programs as ones and zeros in the same memory as the data. To this day, at its core, that's a pun, a computer does just three things. First, load ones and zeros from memory into the central processing unit, or CPU. Second, changes the ones and zeros within the CPU, and finally stores the resulting ones and zeros back into memory. No matter what happens, a computer is simply manipulating ones and zeros. You may type in some code for your video game that looks like this. If x position is less than 800, then x position equals x position plus 5. But at some point, that code must be translated to a sequence of ones and zeros so the CPU can execute it. It's nothing more than ones and zeros. These are the ones and zeros called machine code, or machine language, that the CPU executes. They are the most critical set of ones and zeros that the computer handles. The numeric values 800 and 5 are converted to binary and are part of the machine code and are stored and manipulated as binary numbers. You can think of machine code as a mixture of binary instructions and binary values. Another reason why binary is so important is something called Bitmap Graphics. The images that you see on the screen during a video game are composed of tiny little dots called pixels. Each pixel has a binary code, a set of ones and zeros that represents what color that pixel should display. For example, with 8-bit RGB, red, green, blue graphics, each pixel has a sequence of 8 ones and zeros which represents a dot on the screen. There's a sequence of ones and zeros to represent the color red. It starts with 3 ones. There's a sequence of ones and zeros to represent the color green. It has 3 ones in the middle. There's a sequence of ones and zeros to represent the color blue. There's 2 ones at the end. And every combination in the middle produces a slightly different color. By mixing the colors together, 256 unique colors can be displayed in 8-bit bitmap graphics. In bitmap graphics, every image is composed of pixels or dots, and each dot has a binary code to represent its color. So, a good understanding of ones and zeros is important if you're going to be a computer scientist, but it's especially important if you're going to understand video games and graphics. Don't worry, this course is not going to be just about ones and zeros. There are other courses that will explore them more thoroughly. But a basic understanding of binary is important for all computer science students. Binary numbers. Bi means 2, as in 2 digits, 0 and 1. There is no 3-digit or 4-digit or 9-digit in binary numbers. It's just zeros and ones. We as people, we're used to the decimal numbers, as in 10 digits, 0 through 9. The dec in decade means 10 years. There are 10 digits in the decimal numbering system, 0 through 9. To understand binary numbers, compare decimal numbers next to the equivalent binary number. You can see decimal 2 is binary 0010. You can see decimal 5 is binary 0, 1, 0, 1. You can see decimal 9 is binary 1, 0, 0, 1. You can see in the binary column there are no 2s or 4s or 9s in binary numbers. It's zeros and ones. And everything the computer does and everything the computer processes is composed of a sequence of zeros and ones. You can brute force memorize the decimal versus binary equivalents, but brute force memorization is not a good way to learn. A better way to learn is to understand how binary numbers work and be able to generate the list of decimal to binary equivalents. With decimal numbers, even if you don't know the next number in the sequence, you could always generate the next number simply by adding 1. So 99 plus 1 equals 100. 999 plus 1 equals 1,000 in decimal arithmetic. Do you remember how you learned this? 9 plus 1 is 0, carry the 1. 1 plus 9 is 0, carry the 1. The carry may require another decimal digit, like it does in these two examples. With binary numbers, we can generate the sequence by simply adding 1. But be careful. In binary, 1 plus 1 is not 2. 1 plus 1 is 0, carry the 1. So if we were to start with binary 0 and add 1 to it, the result obviously would be 0, 0, 1. We would start with binary 5, 0, 1, 0, 1, and add 1 to it. Remember, it's 1 plus 1 is 0, carry the 1. So it ends up being 6, or 0, 1, 1, 0. Look at 6, 0, 1, 1, 0. You add 1 to it, and you come up with decimal 7, or binary 0, 1, 1, 1. Now, just to reinforce the thing, start with decimal 7. Binary 0, 1, 1, 1. Notice how when we add 1, 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. And the final carry expands the number of binary digits. So binary 8 is 1, 0, 0, 0. If you look closely, binary 0, 1, 1, 1 plus 1 equals 1, 0, 0, 0. This is not much different than decimal 999 plus 1 equals 1, 0, 0, 0. Another way to generate binary numbers is to know your powers of 2. 2 to the 0 power is 1. 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8. If you write these powers down and backwards, you can see they represent the individual digits. So I'm going to write 8, 4, 2, 1 down backwards, and below it I'm going to put a binary number 0, 1, 0, 1. See the ones under 4 and 1? They represent the numbers 4 and 1. 4 plus 1 equals 5. This tells us decimal 5 is binary 0, 1, 0, 1. Let's do it again. Write down 8, 4, 2, 1. Underneath it, put 0, 1, 1, 1. See the ones under 4, 2, and 1? 4 plus 2 plus 1 equals 7. Decimal 7 is binary 0, 1, 1, 1. You can also work this backwards by subtracting powers of 2. Start with the decimal number 9. 9 minus 8 is a 1. Obviously, an 8 fits into the number 9, so we put a 1 under the number 8. Now, 4 does not fit into the 1 that's left over. 2 does not fit into the 1 that's left over, so we put zeros under 4 and 2. Finally, 1 does match the 1 that's left over, and we put a 1 under there. So, decimal 9 can be converted to binary 1, 0, 0, 1 by again subtracting powers of 2. The final way to generate the binary sequence from 0 to 9 is a simple pattern. If you look closely at the numbers below, the far right column, under the 1, the digits alternate, 0, 1, 0, 1, 0, 1. If you look at the second column, under the 2, every 2 binary digits alternate, 0, 0, 1, 1, 0, 0, 1, 1. If you look at the third column, under the 4, every 4 binary digits alternate. This is not an accident. Remember your powers of 2. 1, 2, 4, 8. This is how often the binary digits alternate. In the first column, they alternate every digit. Finally, what is the point of all this? Why do I teach you 3 different ways to generate binary numbers? Because binary numbers follow clear and simple patterns. Therefore, it's possible to build small, simple circuits to manipulate them. They could build a computer that operates on decimal numbers, but the circuits would be large, complicated, and slow. Because binary numbers follow simple patterns, circuits to manipulate binary are smaller, simpler, and faster. Back to video games. As I said earlier, all executable programs, the machine code, are sequences of binary digits. So when you play video games, you are executing on the CPU these ones and zeros called machine code. All computer software, including video games, are written in a programming language. There are many different programming languages out there, including Java, C, C++, C#, BASIC, PHP, JavaScript, and many, many more. All programming languages must be converted to binary machine code before they can be executed by the CPU. One way to categorize programming language is when does the machine code get created? When is the program converted to binary? A compiled language creates the binary machine code before the program executes. C and C++ are examples of compiled languages. An interpreted programming language creates the binary machine code during program execution. JavaScript and PHP are examples of interpreted programming languages. Compiled languages are much faster because the machine code is already created before you try to run the program. However, that code only runs on the CPU it was compiled for. It generally doesn't work on other computers. If you've compiled to run for Windows PC with Intel compatible processor, the program only runs on a compatible Windows PC with an Intel compatible processor. Interpreted languages, while slower, generally are more flexible, so any computer with an interpreter should be able to execute the program. That is why JavaScript and PHP generally run on any computer system. At runtime, on the fly, the interpreter creates the machine code needed for the CPU. In order to take advantage of the speed of a compiled language and the flexibility of an interpreted language, a new category of languages has been developed that does both. A hybrid programming language is a combination of compiled and interpreted. It compiles to a system-independent code, and then when it's executed, interprets into the binary machine code for that CPU. Java and C# are examples of hybrid programming languages. These languages require the use of software known as a virtual machine. The VM's job is to take a system-independent code the compiler creates and interpret it to produce binary machine code at runtime for CPU the program is executing on. Picking up programming languages versus picking a game console. The absolute best programming language to use is ... Before we answer that question, let's answer a few more important questions. The absolute best game console to buy is Sony PlayStation, Microsoft Xbox, Nintendo. The critics, whoever they are, say the PlayStation graphics and sounds is the best, so that's got to be it. But my favorite game is Halo, and it only runs on the Xbox, so that's got to be the best system. But all my friends have a Nintendo, and I want to be able to trade and borrow games, so that's got to be it. It turns out, which console to buy is not such an easy question. In a simplistic way, you could say it boils down to personal preference. A more scientific approach might be deciding what's more important to you. Say you come up with this list from highest priority to lowest priority. Number 1, I want to be able to trade and borrow games from my friends. I'm low on funds to buy new games. Number 2, I want to play the game or games exclusive to that console. Number 3, I really want good high-resolution graphics. Now compare this list to the list of advantages of each console and determine which system matches your priorities. Back to the question of which programming language is the best. The answer is none of them or all of them. Like the game console, you need to match your priorities to what each language does best. Compiled languages like C or C++ generally run faster. If your highest priority is pure speed, go with the compiled language. Interpreted languages like JavaScript and PHP run on about any computer. If that's important to your project, use an interpreted language. Recently, Java has had a terrible time with security in its web browser plugin. If security is an issue with your project, Java may be a poor choice for a web-based program. However, Java is the go-to language for Android development. If your project is to develop Android phone or tablet programs, apps, Java is the perfect choice. Now, I doubt that a group of carpenters would sit around and argue about what's the best tool to use, hammer, saw, or screwdriver. It's clear when you want to pound something, you use a hammer. When you want to cut something, you use a saw. I better stop there. Yet programmers will endlessly debate. What's the best programming language? There is no such thing. At most, there's the best programming language for the project. Just like a carpenter can't argue that a hammer is better than a saw when he wants to cut something, you can't argue that one programming language is always better than another programming language. It depends on what you're going to do. Again, you create a list. What are the highest priority features required for your project? Let's say number 1 is the program must run from a web page. Number 2 is the program must run on multiple computer platforms. Number 3 is the program must work on our current database. Use the programming languages that matches your list of priorities. If Java is best, use Java. If C++ is best, use C++. It doesn't matter what language you program. It only matters that it does the job you need it to do. A programming language is a tool to accomplish a task. Take the tool best suited for that task. Now, I'm sure the debates over the best game console will concern you. Just as I'm sure the debates over the best programming language will continue. I'm just glad the carpenters have figured out the task at hand determines the best tool for the job. I just wish programmers would decide that the task at hand determines which programming language you're going to use. One last thing before I move on. Generally, it's your boss or the customer that's paying for the project that determines which programming language used to develop the program. The best programming language is the one that earns you a paycheck. Object-oriented programming. There is one type of programming language that I will insist is more important than the others, and that is an object-oriented programming language, also known as OOP. Java, C++, C# are all examples of full object-oriented OOP languages. PHP has evolved into an object-oriented programming language. JavaScript, while not a full object-oriented programming language, has object-oriented features. We'll call it OOP Lite. Since most programming languages are OOP, and the computer science curriculum focuses strongly on OOP, and there are many examples of video games programmed in Java, C#, C++, the second half of this course will spend a majority of its time on understanding and using object-oriented programming. Say you're playing a sim-style game, and the town you're building needs a fire station. Failure to create one may cause your town to burn down, so you've allocated in your budget enough money to equip your station with 2 separate fire trucks. Now, option 1, buy a large water tanker truck, which can carry a huge amount of water to a fire, and then buy a second truck to carry the firefighters, the ladders, the hoses, and everything. Option number 2 says buy 2 identical classic red fire engines, which must carry the water. They have water tanks plus firefighters, ladders, hoses, and everything else on that red fire truck. The first option allows you to get the most water you can to a fire, which is very important. But several things could go wrong. With 2 essential components, water and hoses, on different trucks, if either truck breaks down, you're in trouble. If 2 fire trucks break out, you can split the If 2 fires break out, you can split the trucks up. Even something as simple as they go to opposite sides of the building could cause major delays. The second The second option is going to reduce your water supply. There's no way the water tanks can be very large if the truck also has to carry firefighters' hoses and equipment. So we are going to encapsulate our major components, our water, our hoses, on the same truck. If one truck should break down, the second one can arrive at the fire and start putting it out. If two fires break out, you can split them up. And even if the trucks go to opposite sides of the building, you can attack the fire from both sides. Combining your critical components into the same truck, encapsulating them, costs the fire truck some water, but it is far more reliable and flexible. Object-oriented programming follows this same principle. The major components of any computer program are the variables, the data, and the methods, the executable code. In a non-object-oriented programming environment, they would be held in separate pieces of computer memory. But in an object-oriented environment, the variables and methods are combined or encapsulated into one entity called an object. By combining the variables and methods into an object, code becomes more reliable, more flexible, and easier to use. Typically, it is said that objects correspond to things found in the real world. In this course, objects will correspond to things found in video games. In a playing card game, we might have an object to represent a single card in the deck, and the variables and methods needed to manipulate that card will be found in this object. In a 2D Mario-style game, we might have an object to represent each brick used to build the screen. Many bricks that Mario runs, jumps, and climbs over to complete a level. In a 3D first-person shooter game, each enemy that our hero battles may be represented by an object. So if you're trying to shoot it, and it's trying to shoot you, it's an object. The variables of the object describe what it is. A playing card object would need a variable for suit, heart, club, spade, or diamond. Another variable for rank, ace, 2, 3, all the way to king. That is the data that describes a playing card object, what it is. That would be the variables. The methods of the objects describe what it does. There are actions that we can take with a playing card. Those would be the methods. A single brick may be an object. You could use hundreds of brick objects to build a level screen for our Mario game. Variables of an object describe what it is. For a single brick variable, you might have an X position, a Y position, a width, and a height. This is the information that describes where to draw the brick and what size to draw. It describes what the brick is, therefore these are variables. The methods describe what the object does. We need to draw bricks, move bricks, or even disappear the bricks if Mario has that power. These are the actions, so those are the methods of the object. Object-oriented programming isn't the only way to program. However, it is the most common paradigm programmers use today. In the first half of the course, we'll focus on creating variables, selection statements, and writing methods. It won't focus so much on object-oriented programming, the first half. But the second half of the course will be a full-on object-oriented programming course. Thank you. Good luck. Enjoy the rest of the class.